Okay, so today we're here for Graham Martin's honors thesis presentation, and Graham will be talking about some work that we've been doing together on modeling fluctuations in a pulsed laser system. And his work has primarily been in the development of the model and the beginning stages of working on getting the model and the measurements to agree with one another. So I'll let Graham take things over.
Good morning, everybody. It's a little early. We got a lot to cover, but let's see if we can keep it concise. So, as the title suggests, we're talking about a new numerical model for fluctuations in a single-mode Q-switch laser system. And for anybody in the crowd who didn't know what every single one of those words meant, we have a short section in the beginning to cover that. And then after that, we're going to talk about our specific laser, the equations that we used for our model, the features of our model, and then talk a little bit about what we're getting so far with trying to match these experiments with our model to the actual observed data. So one of the first and most simple principles of laser creation is a bit of atomic physics, which is absorption. Because atoms and molecules can be excited to higher energy states by photons with frequencies unique to them. And once it absorbs it, it jumps an energy state and then becomes excited. And just to nitpick, there are technically no two-level laser systems. Ours is 4, most are 3 or 4. But for simplicity, we're going to leave it like this. And once you have enough atoms in an excited energy state, then you get what's known as a population inversion, where a majority of the atoms are excited with a minority not be excited. And you have to have that in order for any delays at all. We'll talk about it. For us, there are two options that matter that an atom or molecule can do once it's excited to get rid of that energy. It can either wait so long that it wants to return to its ground state and then releases a photon with energy equal to the difference between the energy levels, and then drops down to its ground state, and releases this photon, which can be of some frequency, not necessarily the one that it absorbed, and in any direction at all, which makes it relatively useless. Or they can do the namesake of laser, light amplification through stimulated emission of radiation, where, while it's in its excited state, another photon passes by, disturbs it, and then it releases a photon of the exact same energy in the exact same direction. And in both cases, they then drop down to the lower energy state to be excited again by incoming photons, which in our case comes from the pump laser. Now, stimulated emission is interesting because hopefully then what we get is a cascade effect. We get 2 more stimulated emissions, and then 2 more, and it eventually turns into trillions of them in a matter of microseconds simply because of how fast this all occurs. But if you let this just go across the crystal once, because it is traveling across, you wouldn't get that much useful light. So in order to make the laser work effectively, we decided to put a mirror on either side of the cavity. So we have one on the left, which is a very high reflectivity mirror, which is very reflective at the laser wavelength, but also very transmissive at the pump wavelength, which is what's providing those photons to excite the atoms in the crystal. And then on the right hand, you have one that's slightly less reflective, called an output coupler. Now, it's not that much less reflective, it's just 95%. So 5% of the photons get through, 95% don't, but that's okay, we want that. Because then we get 95% of them able to go back in the cavity and give their contribution to more stimulated emissions. And if we have a couple spontaneous emissions along the way, it doesn't matter, they just leave the cavity. And it doesn't matter, we don't need them, we don't want them, so they can leave. And eventually, very quickly, you have almost all coherent light within the cavity and leaving the cavity, which means it's in the same phase and of the same frequency. This is where you're getting lazy. But, as the title suggests, that's not quite enough. This last laser cavity only gives continuous wave, just a normal laser with no pulsing, and is not necessarily single mode. So in order to do that, we have to add 2 things. An etalon, which allows for single mode operation, and an acousto-optic modulator, which allows for pulsing. And just a nitpick here, for us, the high reflective mirror is actually the edge of the crystal. So the etalon is very simple. It's just another cavity. It's 2 mirrors that are very close together. So close, in fact, that only certain standing waves can get through, certain modes. Which a good analogy for standing waves is just 2 wooden dowels with a string in between it. You pluck it and it makes a wave, or you pitch it and pluck it again and it makes different waves. This is so close together that only certain modes can fit in. And what this is really doing is adding an extra constraint to the cavity. Because normally there are lots of modes going on within the cavity, all that fit underneath what's known as the gain curve. And this just adds an extra constraint. Because all the modes want to win out of the other, but normally they can't. So this gives it 1 so that 1 can win. Pulsing, very simple. The acousto-optic modulator is just a piece of glass that has sound waves pass through it. And this disperses light. When the losses are high, the waves are turned on, and so almost nothing's getting through. A little bit is, which we'll talk about in a minute, but most of it's not. And then all of a sudden, for just a moment, we turn off the losses as much as we can. And for us, a window of about 4 nanoseconds. And in that space, all the energy that's been building up cascades out like a dam being broken. And then we turn the losses back up again. And what's interesting about pulsing is that unlike continuous wave lasers, this allows for a much higher peak power than what we would normally get with a continuous wave laser. The definition of power is joules per second, and if we decrease the amount of seconds for the same amount of joules, we have a much higher power. For CW, it could be something like 7 watts. For peak pulsing, this can get over 1,000 watts. This is 2 orders of magnitude increase. Well, actually 3. It's a big deal. Now, like we said before, the losses are turned up high, but not all the way. There is still a small amount purposefully left to go through it, known as prelays or relaxation oscillations. And very simply, this is the seed that feeds the laser. This is what decides what the single mode is going to be. It oscillates very quickly and then settles out. But what this does is it doesn't always settle out the same. It doesn't always settle in the exact same place. And that means different modes, different frequencies, which because of how transmissiveness works on mirrors means different powers being lit up, because not all frequencies transmit the same. Now this is a picture of relaxation oscillations at 1,000 hertz up close. And this is one at 200 hertz, which, if we were to extend this out, would look a little different, because this is just a little bit quicker and allows for, with more time between pulses at only 200 hertz versus 1,000, you get a slightly more, well, really a very more accurate prelays. With more time, it tends to settle closer to the same place. With less time, it settles further away from it. That should make sense. Now let's talk real quickly about the equations we use. We have 2 primary variables that we wanted to model, which are the change in population inversion, dn over dt, which is nothing more than the number of excited atoms over time, and the change in power, which is pretty explanatory. Some of the important things here, though, perhaps the most important variable, the most important one, is time dependent, and that's losses, which is made up of more or less 3 distinct parts. The time-dependent losses come from the AOM, because as we know, it changes over time from high to low. The ones induced by the output coupler, because once again, only 5% make the group. And ones induced by the etalon, because by cutting out certain frequencies, we are losing some power through the etalon, because not everything can make it through. It is an extra constraint, like we talked about. Some of the other things to talk about are, for instance, tau, upper state radiative lifetime. That's nothing more than how long an atom, on average, will stay in its upper state before it decides to spontaneously jump back down. It can be affected before that, but that's on general, how long it stays if it doesn't get stimulated. Tau sub OC, which is simply the time on average that a photon will stay in the cavity, bouncing back and forth before it leaves the output coupler, or the other end. It can leave through that, but it usually doesn't. Gamma, which is the net single pass logarithmic losses, which is just on average what you're going to lose in terms of power on one pass through the cavity. X, which is the normalized pump parameter, which has no units because it's a ratio. It's a ratio of the power we're supplying through the pump, which gives that energy to excite the atoms, divided by the power that is minimum necessary. Because if you don't have a certain amount of power, you don't achieve population inversion. That's known as the threshold. So it's nothing more than how much we're giving it versus the absolute minimum to get anything at all. H is Planck's constant. And B is stimulated emission rate coefficient, which is, simply put, how big an atom looks to an incoming photon that wants to stimulate it. The bigger the better, the smaller the worse, because it makes it more or less likely that we're going to get a stimulated emission. Nu is just the frequency of the laser, which in our case is 282 times 10 to 12 hertz, or 1064 nanometers if you want to change it into wavelength. Alpha B, which is the optical length of the laser cavity, which is different than the physical length. Because even though to us we can put a ruler down and measure the length of the cavity, to an actual photon it looks different. Because certain pieces of equipment actually look longer than just air to photons. And C is the speed of light, 3 times 10 to the 8 meters per second. Let's talk about these equations individually. For the change of population diversion, this looks pretty complicated, but in reality it's pretty simple. You have the positive term, which is feeding it, the pumping, because for all the energy coming in, you're getting a population diversion, you're getting more atoms excited, and so this is your positive term. And any emission at all decreases from that population diversion because each emission of any type drops an atom back down. So it's that simple. This gives you your base, and this subtracts from it. And the stimulated emission, of course, has a very specific frequency there, so that's given there. Pretty simple ideas. Oh, and by the way, just a quick nitpick for anybody here who likes math. These are nonlinear coupled equations that we used RK4 to solve for, so which go there. The next bit is power. And in this case, it's actually opposite. We have only one term that detracts and two terms that add. So for this, the largest term, as you can imagine, given the acronym for laser, is the stimulated emission term. Because the majority of because all these are in the axis of the cavity, aren't trying to leave the axis, can actually go through the mirror. And you occasionally will have a spontaneous emission that goes the right direction. Nothing says that you can't have a spontaneous emission that isn't of the right frequency and isn't along the cavity. That can happen, but it's really rare. It's in once per pass, 1 out of trillions of trillions of trillions of photons. But it is necessary to put there because it is an important part of the model. And then the negative term is, of course, the losses. It's what's induced by the AOM itself. When the losses are high, power output is low. When the losses are low, power output is high. Simple as that. What we also had to do, though, was add to our model the ability to have multiple pulses, because while looking at one pulse is fun, it doesn't give us a very good sense of the fluctuations. We need multiple pulses to compare to each other in order to find them. And that was really simple programming-wise. All we did was create a for loop that fed the final values of the pulse back into the beginning as the initial values of the prelays for the next pulse. Really simple idea there. So if we go back to an old graph that we had for the AOM, it now looks like this. High losses and low losses, just these tight peaks. Which in terms of scale, this would be very, very small, but it's hard to see when you're talking about microseconds versus nanoseconds. And then one more thing we had to do was, if you notice, these look like square pulses. It looks like things change instantaneously, but it doesn't. There actually is a shape to the losses. And this sort of happy midway that we found between easy implementation and accuracy to life, for us seemed to be a half cosine. So the high losses would be up here at the top and the low losses at the bottom. And for anybody who nitpicks about math, you'd say, but Graham, this jumps back up to the top immediately. Wouldn't that be instantaneous? True, but there's so little going on there because the losses are so, because there's really not going on here very much. So that switch is really negligible in terms of its effect on the overall model. So we decided that for implementation's sake, that'd be a pretty simple thing to ignore. Now, loss switching also has an effect on the pulses themselves because of the way that the pulses form. For short loss switching, you're going to see very high peak powers and a very thin pulse, which should make sense because it's happening over a short period of time, and generally with a shorter switching time, it means the pulses will form after the switching, which means it's being affected by the lowest possible level of losses, which means it's not affecting the peak. But if we increase the time, we see a difference now. That went from 1,000 to under 500. That's a decrease of half, because now the chances of the pulse getting caught during the switching period are high. So if it gets caught earlier on in the switching period, that means it's experiencing higher losses, which means we get a lower peak power, as well as a wider base here, because it's happening over a long period of time. And this increases again when you increase it more. This happens over and over again, until now it's another decrease of half, and it's much, much more noticeable here in terms of increase of width. But there are also effects on a much more macroscopic scale, on pulse ensembles, not just single ones. We see that with changes in switching time, we see a change in how fast the transients die out, which transients themselves are like that. The transients are not permanent. It's just the first couple, 10, 20, however many pulses you have that decide to not really settle in at the beam of the laser. And generally, with the lower switching time, you have quicker dying out transients. And you'll have, because of the switching time being low, a pretty similar peak time, because if most of the pulses are forming after the switching time, they aren't being affected by the actual change in losses. They're about the same. Now let's increase it a bit. Now we have a very, very distinct slope here. And we have really what is harder transients. It takes a bit longer for them to die out. And this sloping should make sense because now we're having pulses forming during the switching period, which means that they're experiencing higher losses. And where exactly the laser decides to settle could be during this could be the switching period. That's not necessarily our choice, but that is how it affects it. We increase it again. Look at this. Now we have 0.5 microseconds, and we see even more transients. We see even more variance in the peak heights because now we have a very long period of time over which the laser can choose to make its pulses. So we have a lot more variance in the actual peak times. Now, the actual features of our model, the most important part, and I know we've discussed all the earlier bits, is the actual perturbations, which we induce by adding sources of noise. Because if you look here, this is real data. This isn't one single laser pulse being overlain 5,000 times. There's a huge change here. There's a huge difference. There's even a change in the shape of the laser pulse itself. This isn't just your perfect laser pulse that's just overlain. So we have to find a way to induce that same sort of fluctuation in our model in order to make it accurate to real life. So we chose two noise sources for this, one of which is distributed and based upon Gaussian white noise, and this affects the relative pump rate, and one source which is lumped and periodic, which affects the losses. This first source is distributed, and distributed means nothing more than it's applied on more than a simple pulse-to-pulse basis. It's applied within the pulse. It can be every 5 steps, every 10 steps, every 100 steps, but for us, it's every single integration step, every data point. And this is based upon Gaussian white noise, which for us doesn't mean too much, but it's a slight fluctuation equal to some user-decided percentage on top of what you normally see for the pump rate. So this is a pretty good way to explain it simply. You have the average pump rate, then you modify it with a percentage. 1 plus, let's say, 3% of whatever this random number is, equally distributed between more or less -1 and 1. So let's say that this was some number below 0, now we have a decrease from the average. Some number above 0, now we have an increase above it, at a maximum of 3%. And a minimum of 0. It could be 0. Nothing could happen at all. It generally isn't, but it could happen. And this has an effect on the pulse ensemble itself. We see a slight sloping to the right, a slight decrease where we get a little bit of this shape here. We get a bit of a time change here. And we also get a change in the standard deviation of the peak times. Every noise source at least slightly negatively affects the standard deviation, which is okay, because don't forget, we need it to be wider or smaller. And so changing the noise allows us to affect that. Now our next source is lump noise. And this applies every cycle, only every cycle, not within it. And it has a periodic component because we found by running a fast Fourier transform, which points out strongly correlated frequencies, things you'd see that really are periodic, and we found it to be around 50 hertz. And we found this noise by sampling that frequency that we found, which is low frequency of let's say 50 hertz, over top of the frequency of the laser itself. So here you see this would be the noise source, and every time it intersects, that would be the number between -1 and 1 that we use to modify the losses. This has an even more drastic effect on the geometry of the pulse ensembles. We see a really serious sloping down to the right, very strong. And once again, a decrease, or rather increase, in the standard deviation of the pulse rate, which is fine. Okay, now that we've talked about that, let's talk about some actual attempts to use this model to try and meet the observed data, to meet the actual data we found, and trying to make these match in a meaningful way, in terms of both the width and the shape itself. So here's one at 1,000 hertz with no noise. As you can see, it's pretty close. In reality, these are just a couple transients, and the standard deviation is very, very small. Up here in this observed data, it's around 4 nanoseconds. Here it's just 2. It's not very much. We need to change things. We need to increase this width and hopefully keep this shape here. It's pretty close, but maybe we can get that activated. Let's see if we can. So we had a 1% distributed and lumped. For most of the experiments, I tried to keep the ratios of the noise in check. I tried to keep them about the same. So we see an increase in standard deviation. That's good. That's good, because originally we didn't have the width we wanted. So we did get an increase closer to the norm. That's fine. We also see a slight shift here. So that's okay for now. That tiny change doesn't mean a complete defeat of the model, but it's something to pay attention to. Increase it again, 2%. Okay, now it's a little different. Now if you remember, up here, it was just 4. Now it's 6. It's kind of a lot, right? So there's a problem here. We have a big sloping, but we have a closer width. This doesn't mean that this model's bad, it just means that now we see some of these limitations. And let's take it even further, just for curiosity's sake, let's increase it more. Standard deviation even higher. And now we see a less smooth peak, let alone just the sloping here, with more transients and less correlation. And in general, it's pretty wide. The shape is okay, and this is good, but not quite perfect. And then a couple times I decided, well, let's change up the ratio, see if there's any major change here. In general, the standard deviation changes depending upon how you change the ratios, but there's not that big of an effect on the shape of the pulse itself. Now that could change depending upon how strongly you change the ratios, but you can't just change them that ridiculously. Certainly I could up the noise to 25 or 50%, but in reality that's not very feasible. It's not plausible. And if your model can't actually find good predictions with accurate numbers that could happen in real world, it doesn't matter. So we had to stay around a feasible noise level without overdoing it, and in order for this model to even matter. Let's take a look at 200 hertz, another side of the scale. This starts off with a much lower spread, a much lower standard deviation, and a different shape up here with that horn being almost completely gone. And just look at that, much tighter spread, which we should expect, because as remember, there is less deviation in the lower frequency because it has more time to settle, and so it's a little more accurate. Here's with no noise. This is pretty much the picture of what you would want a laser pulse to look like, a laser pulse ensemble in a perfect world. There'd be no noise variations at all. It would just be one pulse overlaid on top of the other because there is no noise, no fluctuations, no perturbations, nothing. With no noise, it's pretty much what 200 hertz is. With that much time to settle out, there's really not many transients to be spoken of. This can't even really measure the standard deviation all that accurately. Certainly it's more than 0, but MATLAB doesn't notice it. Let's add 1%. We're getting somewhere. We're not even close to actually being to the actual standard deviation, but we have some better spread. And the shape of the pulse ensemble itself is still acceptable. More than that, really, compared to the original data. Up and again, 2%. Now we're getting somewhere. We have a much wider pulse strain. This is much more similar. This sloping here is okay. We're still getting a decent shape. This is fine. Standard deviation closer. And up to 4%, standard deviation didn't change so much. It actually went down a little bit, which could just be an effect of running it multiple times. I mean, this is stochastic in many ways. This is not the same pulse strain every time. If you run it enough times, you're sure to find at least a couple outliers eventually. That's just how this works. But we're getting a better spread. We're getting groupings around the periodic noise itself, which can happen. But that's really about what we figured out right now. There are more things to fine tune, but and I did do some ratio switching, but there really wasn't a major effect on 200 hertz, so I just decided to leave it out of this. But that's about it. I mean, I hope you learned something here, but we've still got a couple things to work on. There's still some things we can play with, because like we said, there are many variables in this. There are things we can change. Not to extremes, but we can look at. For instance, we're still looking a little bit at fine-tuning the actual loss switching time, because it has the opposite effect in most of the noise sources. And while we can't change this a lot, we can change it a bit to see what we want to get. There's still a lot of work to be done. Well, not a lot, but a bit of fine-tuning, a bit of things we don't quite know. This is really just the beginning of a larger body of work. So with that, that's my spiel. If anyone has any questions, feel free to ask.
So yeah, so open for questions now, and I'll ask the first question, and that is, can you tell them what single mode means, and try to give a good definition of that? I think some of them may not have understood that.
It is, at least for me, a difficult concept to explain in an approachable manner. So the idea of
what it is, not how it occurs, but what it is.
Okay. What it is that normally within a laser, you have multiple frequencies that are very close together, fighting for dominance. And normally this doesn't happen. Normally most of them can't win out, or if they do, it's only for a split second. So what we want is just one frequency. This is really just one frequency. There can be tiny dithering in it, but one frequency as opposed to multiple fighting for competition within the laser cavity. So what's coming out is just one frequency. Not a lot of them fighting, but just one. One standing wave.
You want to put it in everyday language, one color, as opposed to a range of colors. So other questions?
What was the range of your laser? What frequency?
Well, it's dithering around 1064 nanometers. That's the main code that comes out. So it's around that there within very, very tiny shifts. I mean,
Are you thinking of the line width? About 100 megahertz, maybe something.
oh, yeah, that I didn't understand. Yeah.
You mentioned the white noise. What typically generates your white noise?
So, wait, do you mean the process that we use to generate it, or why we decided on white noise?
Both. Well, I know white noise is probably from background.
Yeah,
I
so,
make that assumptions, but what would you, talking to a non-physics major, what creates some of that background noise that you're worried about?
so in the relative pump power, this could be a lot of things. So, first start with how we found it. So, we took a power meter and just put it in front of the pump laser. This is before the rest of the cavity, just looking at the pump. And we found little dithering in it, little shifts. And you know it's white noise when if you change the scale, change the time scale, the dithering looks the same. Because Gaussian white noise doesn't have a scale. It looks the same no matter what scale it is. So we decided it was white noise. We decided to, what creates it? Well, there could be a lot of things that create this effect. So we decided it was white noise. That was the first step. What could be creating it? A lot of things. Gaussian white noise is up to be a combination of factors. One of the most common ones I can think of would be just shifting in the power supply itself. I mean, that could be low frequency or high frequency, but there's a lot of outside factors that can add to this. It could be a smattering of things. It could be one thing. It's kind of hard to pin down, which is part of the difficulty of making models to begin with, is finding what all these variables are. The main one that I can think of would be, I mean, I don't know if you think mechanical noises could really play a part in that, but I mean, dithering in the power supply can be.
Mechanical probably manifests itself in other ways.
Yeah.
Electrical noise, what you get from the power supply.
Yeah, there's a lot of things. That's the main one I can think of that would create that. If that was what your question was.
Yes, yeah, I was just trying to understand it and where that comes from.
Sure. I hope that was an okay explanation.
What you say?
Oh, yeah, you would want.
Okay, so you found a model that's telling you what you should expect.